Good morning, students. Good morning. Today we have lecture number 11. Lecture number 11 on fluids. Lecture number 11 on fluids. In the previous lecture, in the lecture number 10, we have studied about the surface energy. We have studied about the surface energy and excess of pressure. We have studied about the surface energy and excess of pressure, and we have calculated the excess of pressure for liquid drop, and I given an homework, that is excess of pressure for liquid bubble or soap bubble, both are same. So excess of pressure for bubble, hope you have calculated it, hope you have derived it. So now next concept, angle of contact. Next concept, angle of contact. Okay, let us study about the angle of contact. The liquid surface usually in contact with the solid surface. The liquid surface in contact with the solid surface usually have the curved surface. And the nature of the surface, nature of the meniscus or nature of the surface depends upon the relative strength of adhesive force and cohesive force. The nature of the surface, that is the particular shape that the liquid takes when it is in contact with the solid surface, that depends upon the relative strength of adhesive force and cohesive force. So now, if adhesive force is greater than the cohesive force, then the liquid wets the solid surface and has a concave meniscus. It is general, we have studied already. Okay, so that is water wets the glass surface. Why water wets the glass? In the first period of surface tension only we have studied. Okay, if adhesive force is greater than the cohesive force, then liquid wets the glass surface or liquid wets the solid surface, and the meniscus will be a concave meniscus. That is the surface, the free surface of the liquid will be a concave. Okay, now if adhesive force is less than the cohesive force, then liquid does not wet the solid surface. And the free surface of the liquid will be convex. That is the shape of the liquid, that is the meniscus obtained will be a convex meniscus. The meniscus, that is the free surface of the liquid, will be a convex. Understood? So now, if adhesive force is equal to the cohesive force, then the free surface of the liquid will be a plane surface. So understand, the shape of the liquid surface when it is in contact with a solid surface depends on the relative strength of adhesive force and cohesive force. The shape of the liquid surface when it is in contact with a solid surface depends upon the relative strength of adhesive force and cohesive force. If adhesive force is greater than cohesive force, then the liquid surface, that is the meniscus, will be a concave meniscus and liquid wets the solid surface. So like this you can understand. Now the concept, angle of contact. So what is the angle of contact? So the angle of contact, I will tell the definition. The angle of contact. The angle of contact is the angle made by the tangent drawn to the liquid surface. The angle of contact is the angle made by the tangent drawn to the liquid surface at the point of contact with the solid surface inside the liquid. Listen to the definition properly. Angle of contact is defined as the angle made by the tangent drawn to the liquid surface. The angle made by the tangent drawn to the liquid surface at the point of contact with a solid surface inside the liquid is called as angle of contact. Understood properly? This is tricky definition. The angle made by the tangent drawn to the liquid surface. Tangent has to be drawn to the liquid surface at the point of contact with the solid surface, where the liquid surface and solid surface contact. From that point, you have to draw a tangent to the liquid surface, and that tangent makes an angle with the solid surface. That angle which is inside the liquid, that angle is called as angle of contact. Understood? This is one way of explaining the definition. Another way, we will tell another definition. Angle of contact is the angle made by the tangents drawn to the liquid surface and solid surface. You draw two tangents. One tangent to the liquid surface and another tangent to the solid surface. One tangent to the liquid surface, another tangent to the solid surface, like that. So, the angle made by the tangents drawn to the liquid surface and solid surface at the point of contact with the liquid surface, at the point of contact with the solid surface inside the liquid is called as angle of contact. So, instead of drawing two tangents, I am drawing only one tangent at one point of contact. Okay. At one point of contact, you can draw two tangents, or you can draw only one tangent to the liquid surface. Okay. Once again, I will tell the angle of contact by using the diagram. So, first understand the diagram. This is liquid. This is a glass vessel. This is a glass vessel or glass tube. The glass tube. Okay. In this glass tube, there is a liquid. This all things are water. Water is there. Okay. So, now the surface, the free surface of the water will be like this. When you view it through a microscope, you say view it through a microscope. If you see it ordinarily, it won't be like this one. It will appear like plane. So, you will be keep on asking, sort of road line. So, practically, so now when this tube is very, very small, okay, we will tell in the next concepts, okay. So, now this is the liquid surface, free surface of the liquid, free surface of water, and this is glass surface, okay. So, now I am telling definition for angle of contact. Angle of contact is defined as the angle made by the tangent. Angle of contact is defined as the angle made by the tangent. This is tangent. Angle made by the tangent drawn to the liquid surface. The angle made by the tangent drawn to the liquid surface at the point of contact with the solid surface inside the liquid. The angle made by the tangent drawn to the liquid surface at the point of contact with the solid surface inside the liquid is called as angle of contact. Understood? Here once again. The angle made by the tangent, drawn to the liquid surface at the point of contact with a solid surface inside the liquid is called angle of contact. Understood? Okay. So, now the angle of contact, what are the factors on which angle of contact depends? So, the angle of contact depends upon the angle of contact depends upon the nature of solid surface and liquid surface. The angle of contact depends upon the nature of solid surface and liquid surface. Nature of solid surface and liquid surface. And the angle of contact depends upon the cleanliness of surfaces. Cleanliness of the surface in contact. Whether the surface is clean or it has some dirt. So, the angle of contact depends upon the nature of solid and liquid. Nature of solid and liquid. Cleanliness of the surface. Angle of contact also depends upon the medium above the liquid surface. Angle of contact also depends upon the medium above the liquid surface. Medium above liquid surface. Above the liquid surface, which medium is there? Air medium is there, or some other gaseous medium is there, or some other liquid is there. So, which medium is there in this region? There, that also this angle of contact depends, and angle of contact also depends upon the temperature. Angle of contact also depends upon the temperature. So these all are the factors on which angle of contact depends. So angle of contact depends upon the nature of solid and liquid. Angle of contact depends upon the cleanliness of the surface, and angle of contact also depends upon the medium above the liquid surface, and angle of contact depends upon the temperature. Okay, so now let us consider this diagram. So now here, when water is poured in a very fine bore of a glass tube. Okay, so now here we observe that the angle of contact between water and glass is acute. The angle of contact between water and glass is acute, that is less than 90 degree. The angle of contact between water and glass, the angle of contact between water and glass is acute, that is less than 90 degree, and the free surface of the liquid has a concave meniscus, and the water wets the glass surface, and generally the angle of contact between water and glass is about 8 degree. The angle of contact between water and glass is about 8 degree. Understood? So now, when mercury is brought in contact with the glass, the angle of contact will be a obtuse angle, that is greater than 90 degree. Angle of contact will be greater than 90 degree, that is obtuse, because mercury does not wet the glass surface. That is, adhesive force is less than the cohesive force. When adhesive force is less than the cohesive force, then liquid does not wet the glass surface, and the meniscus obtained will be a convex meniscus, and the angle of contact is greater than 90 degree, and the angle between the mercury and glass is 138 degree. Generally the angle between the mercury and glass is 138 degree. Understood? Okay. So now, when the pure water is brought in contact with pure silver vessel, the free surface of the water will be a plane, that is the angle of contact will be 90 degree. Understood? So this is concept of angle of contact. Understood? Okay. So now the next concept. So shape of liquid meniscus in a narrow tube. So next concept we will study. Now let us study the shape of liquid meniscus. In a narrow tube. Just for your understanding, I am telling all these things. Shape of liquid meniscus in a narrow tube. Okay. So consider a liquid molecule O at the point of contact with the liquid and solid. Consider a liquid molecule O at the point of contact with the liquid and solid. The various forces acting on that molecule are as follows. That is the surface tension between the liquid and vapor. That is, this is air or vapor. The surface tension between the liquid and vapor acting tangentially to the liquid surface. The surface tension between the solid and vapor. The surface tension force between the solid and vapor acting parallel to the solid surface. The surface tension force between the solid surface and liquid surface. This is solid and this is liquid. The surface tension force between the solid surface and liquid surface acting parallel to the solid surface and below the point O. So now similarly here also. So now the another force, that is adhesive force. The adhesive force acting at the point O, acting on the molecule O, is perpendicular to the glass surface. Perpendicular to the glass surface, that is Fa, the force of adhesion. So now when the surface tension, that is the force due to surface tension between liquid and vapor, the force of surface tension between liquid and vapor is resolved into two component, that is TLV sin theta, and TLV cos theta. So here it will be TLV cos theta and here it will be TLV sin theta. Then we find that for the equilibrium of this point O, for the equilibrium of the molecule O, the force of adhesion must be equal to, that is TLV sin theta, and TSV, that is force of surface tension between a surface, that is solid surface, and vapor, is equal to TSL, that is the force of surface tension between solid and liquid, plus TLV cos theta. Understood? So therefore we can write TLV cos theta is equal to TSV minus TSL. So therefore cos theta is equal to, you can write the formula TSV minus TSL divided by TLV. So this is the formula for to find shape of the meniscus, So the shape of the meniscus depends upon the angle of contact. So it is if first point, if TSV is greater than TSL, that is the force of surface tension between solid and vapor is greater than the force of surface tension between solid and liquid, then theta, then cos theta is positive, then theta will be less than 90 degree, that is acute angle, So in this case the meniscus formed will be, that is concave in shape, because theta has to be, angle of contact has to be less than 90 degree, then liquid wets the solid surface, understood? If TSV is greater than TSL, then cos theta is positive. The cos theta will be positive, and that is theta is less than 90 degree. That is theta, angle of contact will be acute. And the liquid wets the solid surface. Understood? So now, if TSV is less than TSL, that is force of surface tension between solid and vapor is less than the force of surface tension between solid and liquid, then cos theta will be negative. Then cos theta is negative, means theta is obtuse angle. That is theta will be greater than 90 degree. So that is the meniscus, the shape of the meniscus will be convex upward. Convex upward, and the liquid does not wet the solid surface. Here liquid wets the solid surface. Understood? So now next one, so last one, if TSL, that is if TSV is equal to TSL. If TSV is equal to TSL, then cos theta will be equal to 0 degree, then theta will be equal to 90 degree. That is theta is 90 degree. Got the idea? So this is how we can explain the shape of the meniscus in a narrow tube. The shape of the meniscus in a narrow tube can be explained by using the angle of contact. That is cos theta is equal to TSV minus TSL divided by TLV. Remember this formula. All these things are not for theory. These things particularly for CT or NEET exam, JEE exam. So like that, so they will ask just for your understanding. Right now only I explained all these things. So try to understand this one once again, then it will be better. Okay. So it's very simple. That's like resolution of a vector. So you know how to write these formulas. So once you study the laws of motion, then you will understand how to write these things. So the forces in the same directions are equated. The forces in the x-axis are equated and forces in the y-axis are equated, and the net force on the point O, on the molecule O, must be 0 for the equilibrium. Equilibrium means for the molecule O to be there only. For the molecule O to be there only, the net force on that molecule must be 0. That is the net force. What are the different forces acting on that molecule? The different forces acting on that molecule are these: TLV, TSL, TSV and force of adhesion. And when we resolve this TLV into two components, so you will get force of adhesion will be equal to TLV sin theta and TSV will be equal to TSL plus TLV cos theta. Vertical component, this is horizontal component. Understood? Okay. So it looks like difficult, but once you study the laws of motion like that, how to write these equations, then it will becomes very easy. Okay. Hope you understood this concept. So now next we shall study about the capillarity. So now we can understand about the capillarity. Capillarity. Okay. So we have heard about capillary tube already while studying about Poiseuille's equation. What is capillary tube? A glass tube of very fine bore. A glass tube of very fine bore is called a capillary tube. That is, if the bore will be of size of the hair. It will be of size of the hair. Hair like size of hole will be there inside the glass tube, and that glass tube is called as capillary tube. Okay. So now capillarity. So when a capillary tube is dipped in a liquid, when a capillary tube is dipped in a liquid, the liquid level inside the capillary tube either ascends or descends. When a capillary tube is dipped in a liquid, the liquid level inside the capillarity, that is the liquid level inside the capillary tube, either rises or falls, and this action, this phenomena we called as capillarity. It is called as capillarity. That is the rise or fall of liquid. The rise or fall of liquid inside the capillary tube. The rise or fall of liquid inside a capillary tube compared to surrounding. Compared to surrounding is called capillarity. The rise or fall of liquid inside a capillary tube compared to surrounding is called as capillarity. Understood? So now, when a capillary tube is dipped in a liquid which wets the glass surface, when a capillary tube is dipped in a liquid which wets the glass surface, the liquid level inside the capillary tube rises. The liquid level inside the capillary tube rises. Remember this. The liquid level inside the capillary tube rises when a capillary tube is dipped in a liquid which wets the glass surface. So now, when the capillary tube is immersed or dipped in a liquid which does not wet the glass surface, when a capillary tube is immersed in a liquid which does not wet the glass surface, then the liquid level inside the capillary tube depresses. The liquid level inside the capillary tube depresses compared to surrounding. Compared to surrounding, the liquid level inside the capillary tube will be depressed if the liquid does not wet the glass surface. If the liquid wets the glass surface, the liquid level inside the capillary tube will rises, and the rise and fall of the liquid inside the capillary tube is called as capillarity. Understood? So now let us see some examples related to this capillarity. That is examples of capillarity action or capillarity. Ink rises in a blotting paper. Ink rises in blotting paper due to the capillarity. The ink rises in blotting paper due to the capillarity. The towel soaks water. Towel soaks water due to the capillarity. And oil rises in a long narrow in a long narrow wick, thread of wick. Oil rises in a long narrow threads of wick due to the capillarity. See here. Ink rises in a blotting paper due to the capillarity. Towel soaks water due to the capillarity. And oil rises in a long narrow threads of wick due to the capillarity. And the sap, ascent of sap. Have you heard the word ascent of sap in biology? It is sap rises in the roots of the tree. The sap rises in the roots of the tree to the leaves and flowers. So this is also due to the capillarity action. This is also due to the capillarity action. See here, actually, for example, the wick is there, a long narrow cotton wick. That is a cotton wick is there. So when it is lightened, the oil rises in this long narrow thread of wick. See here, actually a object cannot move on itself against the gravity. A object or a mass cannot move against the gravity, but here the oil or the water or sap, if you take, it is rising. It is rising against the gravity. It is rising against the gravity. That is, sap rises inside the roots, whereas sap is that is nothing but a mass, that is liquid. Water, so it does not supposed to rise. It does not supposed to rise against the gravity. So if it rises on itself against the gravity, so it will be failure of laws of motion, failure of gravity or failure of laws of motion. So force is in the downward direction, then also the oil is rising in the threads of the wick. So that is due to the capillarity. That is due to the capillarity. That is due to the excess of pressure or surface tension. You can tell due to the excess of pressure or due to the surface tension, the oil rises in the wicks. Oil rises in the threads of wick, or sap ascends in the roots of the tree. Understood? Okay. So now let us study the next derive an equation for ascent, that is ascent formula. So next 5 marks derivation, ascent formula. Ascent formula. I will change these diagrams only. I will change these diagrams only for the better understanding. I will consider this as a glass tube, that is capillary tube. It is a capillary tube, very fine bore. It is very small, but for you people to see, so I am drawing it as very big. For you people to see, I am drawing it as very big, and it is placed in a container. It is placed in a container like this. So that is, so I will take this one, this diagram only. So it is placed in a container. Okay, let us say there is a big container is there, and in this big container there is a liquid. There is a liquid, and this is a glass tube. Open at both the ends. A glass tube of very fine bore. Open at both the ends. It will be open at both the ends. And this is water. This is water. So all these things are not required. Okay. So leave it. Okay, no problem. So this is water, and inside the capillary tube, inside the tube, the water level will rises. The water level will rises. Okay, let us take this water level to less, so that height is seen properly. This is glass tube, and this is surrounding water. So surrounding water is up to here. But inside the glass tube, the water level is raised. The water level is raised. So this is water, and inside the glass tube, the water level is raised. Okay. Okay. So now let us derive the formula for ascent formula. So this is the level of the water, and this is to height. The liquid has rised inside the capillary tube. So now let us consider now I am deriving the ascent formula. Let us consider a capillary tube of radius r. Let us consider a capillary tube of radius r. radius of capillary tube. Capillary tube. And it is dipped in a liquid of density rho. It is dipped in a liquid of density rho. Let us consider a capillary tube of radius small r dipped in a liquid of density rho. Dipped in a liquid of density rho. Suppose the liquid wets the glass tube. The liquid wets the glass tube. Then the level of liquid inside the capillary tube rises. The level of liquid inside the capillary tube rises. So now, due to the excess of pressure, so we know that on the upward of the concave surface, so towards the concave surface there will be excess of pressure. So just in the previous class during studying about the excess of pressure, so excess of pressure exists towards the concave surface. So there will be excess of pressure towards the concave surface compared to this point. So the excess of pressure is given by delta P is equal to 2T divided by R, where capital R is the radius of the concave meniscus, If we draw a sphere with this concave meniscus, that is this concave meniscus, I am drawing the surface as a complete sphere. Okay, so R is the radius of the concave meniscus. So now, due to this excess of pressure, the liquid level will rises. As the liquid level rises, the hydrostatic pressure rises up to what height? So it will rise up to a height that the hydrostatic pressure inside the liquid, the hydrostatic pressure inside the glass tube is balanced, will balance the excess of pressure. The hydrostatic pressure inside the capillary tube, the hydrostatic pressure inside the capillary tube will balance the excess of pressure. The hydrostatic pressure inside the capillary tube is given by rho GH. Rho is the density of the liquid, G is the acceleration due to gravity, and H is the height to which the liquid rises. H is the height to which the liquid rises. We have derived this formula, P is equal to rho GH. That is, the pressure exerted by the raised part of the liquid inside the capillary tube will be equal to the excess of pressure. So liquid inside the capillary tube rises until the hydrostatic pressure exerted by the raised part of the liquid inside the capillary tube balances the excess of pressure. Understood? So therefore we can write the formula. So that is, we will take one more thing, that is, we will try a triangle here. We will try a triangle. So this is the center of this concave meniscus. Center of the concave meniscus. We will try a triangle. So that is a right angle triangle. So this is small r. This is radius. This is center of the concave meniscus. Okay. This is center of the concave meniscus. Okay. This is a sphere. Okay, center of this sphere. Okay, this will be the radius of curvature of this concave meniscus, that is capital R. And this point is at the center of the glass tube. So therefore, from here to here, the distance will be the radius of this glass tube. Understood? This will be the radius of the glass tube and this will be the radius of the concave meniscus. Understood? And if this is theta is the angle, then we can write cos theta is equal to small r divided by capital R. Cos theta is equal to, this theta will be also same. So small r divided by capital R. So therefore capital R is equal to small r divided by cos theta. So therefore this equation 1 becomes, that is, so delta P is equal to 2T divided by capital R is equal to small r divided by cos theta. So it will become delta P is equal to 2T cos theta divided by small r. Call this equation number 2 and this is equation number 3. So now comparing equation 2 and 3, that is, excess of pressure must be equal to the hydrostatic pressure exerted by the liquid column inside the capillary tube. So that is 2T cos theta divided by small r is equal to rho GH, rho GH. So now, so therefore H is equal to, so it is 2t cos theta divided by 2t cos theta divided by R rho G. So this is the formula for ascent formula, that is height of the liquid inside the capillary tube. The height of the liquid inside the capillary tube is given by H is equal to, the height of the liquid inside the capillary tube is given by H is equal to 2t cos theta divided by R rho G, where T is the surface tension, T is the surface tension and theta is the angle of contact, small r is the radius of capillary tube, rho is the density of the liquid, G is acceleration due to gravity and H is the height to which liquid rises inside the capillary tube or liquid falls inside the capillary tube. So if you take the same thing as that is liquid level is falling. So if the capillary tube is placed inside the mercury, that is the mercury does not touch the glass surface, then the liquid level will fall. Then also if you do the same thing, that is the main point here is the excess of pressure due to the curved surface. So whenever there is a free surface of the liquid is curved, there will be excess of pressure. That excess of pressure is equal to the hydrostatic pressure inside the capillary tube. The hydrostatic pressure generated due to the rise or fall of the liquid inside the capillary tube will be equal to the excess of pressure. So if you equate that two equation, we will get the height of the liquid inside the capillary tube. Understood? So now if we compare, if we take the volume of the liquid, present in the meniscus, if you consider, we have not considered while deriving this equation, we have not considered the volume of the liquid inside the meniscus. If you consider the volume of the liquid inside the meniscus, the formula will change as to, H is equal to 2t cos theta divided by R rho G minus R by 3. So this is the formula. If we take the consideration, that is the volume of the liquid inside the meniscus, is taken into account, then the formula becomes this one. So this is a very, very small value because the radius of the capillary tube is very, very small. Radius of the thickness of the hair, cross sectional area of the hair. You understood? So that radius, it will be very, very small value. So neglect that R by 3. So only H is equal to 2t cos theta divided by R rho G is enough. Understood? Okay. So this, from this, so we understood that the height of the liquid or rise or fall of the liquid inside the capillary tube is inversely proportional to the radius of the capillary tube. The height of the liquid inside the capillary tube is inversely proportional to the radius of the capillary tube. The height of the liquid inside the capillary tube is inversely proportional to the density of the liquid. And height of the liquid inside the capillary tube is directly proportional to the surface tension. So thus, what are the factors on which height of the liquid inside the capillary tube depends? That is, the height of the capillary tube depends upon the radius of the capillary tube, density of the liquid and surface tension. Understood? So that means if the radius of the capillary tube is smaller, the height of the liquid will be more. That is, if we take a more narrow capillary tube, that is a narrower capillary tube, then the height of the liquid will be more. If we take a very, very narrow capillary tube, then height of the liquid will be more. If we take a wider capillary tube, the height of the liquid will be less. Understood? So this is a concept of capillarity. This is the concept of capillarity. This is the expression for ascent of sap. So this much ascent formula. So this much derivation is enough. This much derivation is enough in the exam. Did you understood the main theory behind this derivation? The main theory behind this derivation is the excess of pressure. So the liquid surface is curved. So there will be excess of pressure. That excess of pressure will be equal to the hydrostatic pressure. hydrostatic pressure due to the rise of the liquid inside the capillary tube. The liquid will rise inside the capillary tube till the hydrostatic pressure is equal to the excess of pressure. Understood? So that is the point. So using that point we will derive this formula. Understood? Okay. So this completes the theory part of the surface tension. So this much is enough for theory exam. So this much is sufficient. Understood? Okay. So in the next class onwards we will solve the numericals. We will solve some numericals on this all the chapters. That is we will solve numericals on Bernoulli's theorem, we will solve numericals on terminal velocity, Stokes law, we will solve some numericals on the surface tension also, okay, in the next classes.